this episode, we take a practical look at regular expressions because they are one of the most common tools for extracting signal from messy text in operations automation. A lot of real-world data arrives as text, including log lines, command output, configuration fragments, and status messages, and automation often needs to pull out specific pieces reliably. Regular expressions are patterns you define so the computer can find, validate, or transform text without relying on fragile assumptions like fixed spacing or exact positioning. Beginners often hear regular expressions described as magic or as a dark art, and that reputation comes from the fact that small pattern mistakes can produce surprising matches. The operator goal is not to become obsessed with clever patterns, but to learn how to use patterns safely, clearly, and predictably so you can support automation workflows without introducing silent errors. When used well, regular expressions reduce ambiguity by turning vague text into structured signals you can act on. When used carelessly, they can increase risk by matching too much, matching too little, or matching the wrong thing in a way that looks correct at a glance. The focus here is to build a mental model for patterns that keeps you grounded and avoids overcomplication. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A regular expression is essentially a description of what you want to match in a string, and it can be as simple as a literal word or as complex as a structure with optional parts and constraints. The key is to understand that patterns are about intent, meaning you are telling the system what counts as the thing you are looking for. If your intent is to find an IP address, your pattern should reflect the shape of an IP address, not just any numbers separated by dots. If your intent is to extract a timestamp, your pattern should reflect the structure of that timestamp, not just any digits. This is where beginners sometimes go wrong by using patterns that are too broad, because broad patterns seem more likely to match, but broad patterns are also more likely to match the wrong content. In automation, matching the wrong content can be worse than matching nothing, because wrong matches can drive wrong decisions. A safe regular expression is one that matches what you intend and rejects what you do not intend, which is exactly what validation is supposed to do. Think of it as a filter that should be selective, not a net that catches everything. One of the most useful mental models for regular expressions is anchors, because anchors define where a match should start and end. Without anchors, a pattern can match anywhere inside a larger string, which can be fine for searching but risky for validation. If you are validating that a string is entirely a certain format, you want the pattern to cover the whole string rather than a small piece of it. Anchors let you say, the match must start at the beginning and finish at the end, which prevents partial matches from being accepted as valid. Beginners sometimes validate by checking whether something contains a pattern, but contains is weaker than is, and validation usually wants is. For example, a string that contains a valid-looking token plus extra unexpected characters should probably be rejected, not accepted, because the extra characters might indicate an injection attempt or a formatting problem. Anchoring is a simple way to tighten a pattern without making it complicated. On exam questions, answers that include stricter validation often reflect better operational safety. Another key concept is character classes, which are shorthand ways to describe sets of characters like digits, letters, whitespace, or specific allowed symbols. Character classes matter because many automation tasks involve matching structured tokens, and structured tokens are often defined by allowed characters. If you are extracting an identifier that should be alphanumeric, a character class can make that intent clear. If you are trimming unwanted characters, classes can help you identify what to remove. The risk is that a character class can be too permissive, such as allowing characters that should never appear in the token, which can cause your script to accept or capture something dangerous or incorrect. The safe approach is to define the allowed set as narrowly as you can without excluding valid cases. This is similar to parameter validation, where you prefer known allowed values rather than accepting anything and hoping it is fine. Regular expressions are not just search tools, they are boundary tools, and boundaries are what keep automation trustworthy. When you treat patterns as boundary enforcement, your designs become safer and your exam reasoning becomes clearer. Quantifiers are another area where small mistakes create big differences, because quantifiers control how many times a character or group is allowed to repeat. A pattern that matches one digit is very different from a pattern that matches one or more digits, and one or more digits is very different from exactly two digits. Beginners sometimes default to the idea of one or more because it feels flexible, but flexibility without constraint is where wrong matches come from. Quantifiers also relate to drift, because if your pattern is too loose, it might match new formats introduced later that you did not intend to support. That can cause your automation to behave differently after a system update, even though nobody changed your script. Tight quantifiers can make scripts more stable by rejecting unexpected formats early, forcing you to update intentionally rather than silently misparsing. There is a trade-off, because overly strict patterns can break when legitimate variations appear, so you want to be strict on what matters and tolerant on what is truly optional. Good patterns reflect a thoughtful balance between stability and necessary flexibility. In exam scenarios, the safer answer is usually the one that avoids open-ended repetition where it is not justified. Grouping and capturing are where regular expressions become especially useful for extraction, because grouping lets you isolate the exact part of the text you care about. You might want to match a whole line, but only capture one field from it, like extracting a status code from a message. Capturing is powerful, but it creates risk if you capture the wrong group or if the pattern can match in multiple ways. If your pattern is ambiguous, the capture might not consistently refer to the same part of the text, especially when optional sections exist. A safer design is to make your groups intentional and to avoid ambiguous overlaps where the same text could satisfy multiple parts of the pattern. Another safety practice is to keep the number of captured pieces small and only capture what you truly need, because capturing extra pieces increases complexity and increases the chance of misinterpretation later. In operations automation, you want extractions to be boring and stable, not clever and fragile. When the exam asks about parsing or extracting signals, the better option is often the one that clearly defines what should be captured and why. Clear capture intent reduces operational risk. Regular expressions are also commonly used for cleanup, which means transforming text into a more consistent form, such as removing extra white space, stripping unwanted characters, or normalizing formatting. Cleanup sounds harmless, but it can be risky if it removes meaningful distinctions or if it overreaches and changes more than intended. For example, removing all punctuation might seem like a convenient normalization, but it could merge tokens that should remain separate, or it could change identifiers in a way that breaks downstream mapping. Safe cleanup starts by defining exactly what you consider noise, then removing only that noise and verifying that the remaining text still matches an expected format. Cleanup can also be performed in stages, where you first normalize simple issues like white space, then validate, then extract, because doing everything in one aggressive pattern can be hard to reason about. Staged cleanup aligns with the fail-safe mindset, because it makes each step easier to inspect and easier to stop if something looks wrong. It also aligns with log reading, because if you want to extract a signal from logs, you often need to remove inconsistent spacing or bracket characters first. The general principle is that cleanup should be controlled and reversible in logic, not a destructive sweep. A major operational hazard with regular expressions is overmatching, which means your pattern matches more than you intended. Overmatching can happen when you use wildcards too freely, when you rely on greedy behavior that consumes too much text, or when you forget to anchor patterns for validation. Overmatching is dangerous because it can hide errors by producing a match where there should be none, and it can capture the wrong field when multiple similar fields exist. Another hazard is undermatching, where your pattern fails to match legitimate cases, causing automation to miss signals or skip necessary actions. Both hazards have consequences, but overmatching tends to be more dangerous for safety because it creates false confidence. A good operator approach is to think about negative examples, meaning you ask what should not match, and you adjust the pattern so it rejects those cases. This is a kind of threat modeling for parsing, where you anticipate how a pattern could be fooled by unexpected text. The exam will often reward answers that anticipate misparsing and prefer patterns that are precise. Precision is the difference between extraction that supports decision-making and extraction that creates silent mistakes. Regular expressions also interact with performance and reliability because some patterns can be slow when applied to large text, especially if the pattern invites a lot of backtracking. You do not need to memorize performance theory to be safe here, but you should recognize that overly complex patterns can become a risk when processing big logs or large streams of text. A safer approach is often to keep patterns simple, constrain them with anchors and specific classes, and avoid nested optional structures that make many different match paths possible. This connects to the broader automation theme of choosing boring, predictable methods that scale. When automation runs under load, slow parsing can become a bottleneck and can cause timeouts that ripple through pipelines. On an exam, if two options solve the problem, the safer one is usually the one that is simpler and more constrained. Simpler patterns are easier to review, easier to maintain, and less likely to behave unexpectedly. That is what operations teams want. Regular expressions are also part of validation, not just extraction, and validation is where they can improve safety dramatically. If you accept input from a user, a file, or another system, validation patterns can prevent dangerous or nonsensical values from entering your automation logic. For example, validating a hostname format or an environment identifier can prevent the script from acting on an unintended target. Validation patterns should be anchored and should reflect allowed formats, and when validation fails, the script should behave fail-safe, meaning it should stop or request correction rather than guessing. Beginners sometimes validate by looking for the presence of expected characters, but presence does not guarantee structure. A strong validation says the whole string conforms to the expected shape and nothing else. This is also where you can combine validation with parameter design, because parameters are safest when their formats are enforced. The exam often tests this principle by offering an option that validates strictly versus one that tries to clean up input and proceed, and strict validation is often the safer operational choice. The main takeaway is that regular expressions are a powerful way to convert messy text into reliable signals, but they demand disciplined design to avoid silent mistakes. When you use anchors, careful character classes, intentional quantifiers, and clear grouping, your patterns become easier to reason about and safer to rely on. When you avoid overmatching, keep patterns simple, and validate inputs rather than assuming they are clean, you reduce operational risk and improve automation predictability. On exam day, you can often identify the best answer by asking which pattern choice is most selective, least ambiguous, and most aligned with the intent of the task, whether that task is parsing, validation, or cleanup. Regular expressions are not about memorizing symbols. They are about expressing structure and enforcing boundaries. In operations, boundaries are how you keep automation from becoming a source of surprises. If you approach patterns with that mindset, you will not only use them more effectively, you will also be far less likely to create parsing logic that fails in silence, which is the failure mode operators work hardest to avoid.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.